All right, and this one, all right, and this one is a very, very cute algorithm. Very simple. It's been around for a long time. So let me install the right library here where you're going to use the scikit learn library for this one. And this is k-means clustering. So let's make a data set which has three clusters of dots. Okay, let me restart the session. Okay. All right. And then this. Okay. All right. So I made a data set that is 5 Gaussian random dots, a big blurry one here and here, and 3 smaller ones here. And my category, my task is to just separate these into groups. That's what k-means does. It clusters together things, and it does it by a wonderful, simple, effective algorithm. All right. What this is going to do is find clusters. The X's mark the middle of the cluster, and it labels them by if it's closer to the center, it calls it that color. So this is a pretty good job. It's grouped those things into 5 groups, as you can see. And we can see how it works here by going through the step-by-step that got it there. And here's a measure of the error, the mean squared error, so a lower number is better. So minus 211 is a good fit. And here we're going to see the steps that led to it. Okay, what it does is it just picks random locations for the centroids. And then it labels the dots based on this. So here you have 2 centroids. It takes all the dots that are closer to this one than to anything else and calls them yellow. Takes all the dots that are close to this one and calls them green. Takes all the dots that are closest to this one and calls them gray. That's it. And after it does that, it then takes the average of the position of all the dots that it labeled yellow and moves the centroid to there. So this is like a ball on a trampoline covered with nuts, making a dent and then going to where the nuts are heaviest. That's all it does. So this one will just move closer to the center after a few iterations. And this one that was very wrong, after this coloring step, it will have a lot of dots down here and not many up there, so it will move in that direction to here. That's how it works. These centroids just move to the new mean, and then you color it again and move them again. So after a while, they fall into the area of densest dots. When it works very fast, and you get a nice fit. See, this is the error. 599 is bad, 212 is good. The problem is, it's possible that it gets a bad start. If I change the random seed from 5 to 2 here, this will not get a good start. If it's really, really wrong, like putting 3 of them over here and only 2 over here, then it never figures out what's going on. It splits this one in half and it combines these 2 into 1. So you get a bad result like this that didn't really sort them. That can happen if you have an unlucky start. So by default, the algorithm tries 10 random starts and goes with the one that gets the lowest error. That's one way to go. That's one issue. Now, so that's one thing that can go wrong. And here's, of course, the same thing we've seen before. Suppose your scaling is wrong. This x is going up by 1s and x2 is going up by 1s and about the same scale. But if I rescale one of the variables to be 10 times bigger, now this is going up by 10s while this is going up by 1s. And let's see what k-means makes of that. Now you get a terrible fit because remember, you told it that vertical distances count 10 or 100 times more than horizontal distances. So it is not okay to have a center here and make a round cluster. It wants to have these horizontal stripes to minimize the vertical distance far more than the horizontal distance. So once again, this shows the importance of scaling your data. Scaling can really mess you up. Now, the textbook I got this from thought this one was a failure, but I didn't see it that way. Suppose your data set doesn't have nice round clusters like this. It has a more complicated shape. So we'll make the moon-shaped data set here with the blue and the green. We're trying to separate them. And now I'm going to fit a k-means cluster with 8. And if you do that, it will fit them like this. And they say that's a terrible fit because it didn't give you 2 categories, but I think this is pretty good. It broke them up into 8 categories, and I would just put another layer that says anything in these 4 is green, and anything in these 4 is the other color, and that would work. So if you think about using it for a 2-layer process, it's not bad. But of course, the fundamental flaw with k-means is it always wants to have one center and just a circular cluster around it. And if the shape is something different, then it's not going to converge well. All right. Anyway, so this can be used to improve other issues. Let me show you something here. If I go back to the digits data set, consider this problem. Let me just clean out this and start again. All right. Now here's going to be, I have a bunch of images, handwritten digits, and it comes with labels. Okay, so first I'm going to just train a model on the entire list of labeled numbers and see how good it is. This is going to be a logistic regression model with all 1,400 the entire training set of 1,400 images. Okay. Okay, so it's 90.6% accurate when I train it on 1,400 label instances. Now, consider a realistic situation where you get a bunch of images from somewhere and you don't have labels and you have to pay somebody to read those and label them. You don't want to pay people to label all those images. So could you get away without labeling them all? Well, here's what happens if I just train the model on the first 50 images instead of all 1,400 because I only wanted to pay for 50 of them to be labeled by humans. Now I'm down to 75% correct. Of course, I didn't have enough examples to do a good job training the model. So here's what you do. I use a k-means model to form 50 clusters. I'm going to try to see if I can find representative images where only 50 images accurately represent all the different types of images you're going to see in there. So I use k-means to group those 1,400 images into 50 clusters. And these are now not the first 50 images or 50 random images. These are the images closer to the center of each cluster. These are the archetypical images, and all other images are nearly equal to these. So now I pay a human to label these 50 archetypical images. And that's what's here, those particular numbers. And now I can train it on just those 50 representative images. And if I do that, it's now up to 85% instead of 75%. So that's good. But remember, training on all the images gave us 90.3 or 90.5%. So I'm not as good. But what I can do now is I can go back and propagate these labels. I only labeled 50 of them, but I'm going to go find all the images in k-means that are closer to this image than any other and label them all 7 and label these all 2. So I'm going to synthetically reproduce the labels to propagate the labels to all the instances based on those archetypical fits. And after I've done that, then the accuracy goes up to 89% from 85%. So that's good, but I can do even better. Now, what happened here is I found that this is the archetypical 7, so anything close to this, I'll call it a 7. But remember, there might be something that is more like a 1, and it's on the very border between 1 and 7. So I don't really know if it's a 1 or a 7, and I really would rather not label it at all. So now I'm going to remove the outliers. I'm going to remove the 1% of images that are the farthest from the centers of the archetypes, because those are ones where the label I'm guessing is not reliable. So by removing 1% of the images and keeping only the 99% that are closer to the center, I now get up to 90.9% accuracy, which is better than training on the original 1400 set, although only by a little, so that's probably in the noise. So this is why these categorization class techniques like k-means can be very useful in conjunction with other problems. Here it was a way to propagate labels to images without having to pay humans to label all those images. So that's what I wanted to show you.